Yes.
Good. The plan today is to cover 7.1 and 7.2. Not everyone has taken the Chapter 3 test, so we won't review that. However, those of you who have taken it, they've been graded and your grade should be out there, so you should know what your grade is. We'll actually review the test either next time we meet or the following after that, depending on when everybody has completed the test. Are there any questions on anything before we get started on today's material on 7.1 and 7.2?
So will the final be from content from chapter B to chapter 8?
The final covers the entire course.
Okay.
Other questions? Okay, let's go ahead and get started on 7.1. 7.1 talks about systems of linear equations in just two variables. And so some of the things we're going to be concerned with when we have linear equations, remember, a linear equation might be something of the form y equals ax squared plus bx plus c or something. And we can solve for this depending on what we're looking for a solution. We might say equate that equal to 0, and let's find out where this function crosses the x-axis. And some of the things we might want to know is if we're given an ordered pair, where an ordered pair would be x and y as a potential solution, we would want to be able to determine, is this ordered pair in fact on this on the linear equation that we're talking about. So if we're talking linear equations, then we wouldn't have anything greater than a 1 here, would we? So this would be a nonlinear equation if we had an exponent greater than 1. We might want to solve these equations in multiple ways. One might be graphically. And if we have this as y1 and we have y2 as some other set of constants, we might say, well, can we see where these systems, and when I have y1 and y2, I'm calling that a system of linear equations. Now we could have systems of nonlinear equations too if these exponents were greater than 1, and we're gonna talk about those also in this course. But given that we've got a system of two linear equations, we could graph the two and say, well, where do they cross? That might be one approach. Turns out it isn't a very good approach unless the solution falls right on a whole number for the coordinates for x and y. Because if it falls somewhere different than on the xy, if we had another system that went through there, if this were 1, 2, 3, well, it'd be pretty tough to tell graphically where this point is. It's not on 2, it's not on 3. We might have 1, 2, 3 here. And it's going to be difficult to estimate what the decimals are, particularly the 2 decimals. So while graphically is a possibility, it's only going to work rarely, only a few cases. Another possibility is to use the substitution method. And that's where we would solve for one equation, say solve for the y value and plug it into the first equation. I'll take you through some examples of that, what that might look like. And that is an approach that's a realistic approach. Sometimes it's not the easiest approach, but it is an option. And the third method might be something which we could call elimination, sometimes called addition. And here we line up the two equations or more. We might have even more than 2 equations, and see if we can eliminate some of the variables. So those are some of the things we're going to try and determine as we go through looking at systems of equations. So let's see if we can go through some examples. And feel free to ask questions as we go through this. So if I give you 2 equations, such as, let's say 2x minus 3y equals -4, and maybe I give you a second equation, 2x plus y equals 4. So here we have 2 equations. So we're going to call this then a system, and it's of linear equations because these exponents are just 1, aren't they? So we're going to call this a system, and they're linear equations. Okay. Now you might be asked, is, for instance, the location 1 and 2 a solution? That is to say, do those 2 values cross? Are they both cross that same point? If I go out here and say over 1 and up 2, question is, do these 2 equations go through that point? And we could say, well, we could substitute the values in and see what happens. So let's go ahead and do that. Let's just call this equation 1 and this equation 2. And if we take equation 1, and this is the x value, and that's the y value, I could say 2 times the x value, which is 1, minus 3 times the y value, which is 2, equals -4. This equation says that's going to be true if this point is on the line. So let's take a look. So that's 2 minus 6 equals -4. 2 -6, that's -4 equals -4. And that's true, isn't it? So that says that this is a solution. So we were asking the question, is 1 and 2 a solution? And we can say 1 comma 2 is a solution. We've just shown it here. Now we could also plug in another value. We might say is, we could pick, what do we want to pick? Maybe 7 and 6. Is 7 and 6 a solution? We go out here, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. And we're go out here. So we said that 1 and 2 was on the line. And now we're asking, is 7 and 6 also on the line? So this one is true. This one we're going to find out. So we can plug in, can't we? Just like we did above. And we could say, well, 2 times 7 minus 3 times 6 equals -4. 14 minus 3 times 6 is 18 equals -4. Well, that looks good. How about if we plug it into the second equation? 2 times 7 plus y, which is 6, equals 4. That's 14 plus 6 equals 4. 20 equals 4. That's not a solution, is it? That's false. So that says that 7 and 6 is, do that in red here, not. It's not a solution. Okay. Now we could also go up here to the first equation and say, well, could we plug in other values? We could do that and see where they cross, but this, we're just saying, does it cross at 1 and 2? Okay, here we're saying, does it cross at 7 and 6? Okay, questions on what we've done there at all?
So it has to cross through both equations in order to be true.
Yes,
Yeah.
because here we're saying that if we were to graph the lines, we would solve each of these for y, wouldn't we?
Oh, yeah.
We would say, let's see, if we do that first one, we'd say 2x plus 4 equals 3y, divide through by 3, and we get y equals 2/3 x plus 4 over 3. So we could graph that, call that y1. And on the second one, we could say y equals negative 2x plus 4. And we could graph that, call that y2. And what we've shown then is if we put these in our calculator, we ought to be able to cross right here. But over here, 7 and 6, we decided was not a solution for the for these two lines. Okay, does that make sense? Okay. All right, let's try another one. Maybe we're given, let's see, is this thing, it's full, okay. Let's try this. Say we're given two equations. Say we're given 3x plus 2y equals 4 and 2x plus y equals 1. And given these two equations, we're asked to solve. And we want to solve for the unknowns x and y. Okay, so if we're going to do that, we can look at this and say, well, what are the three methods that are possible for solving? We could graph it, which unless only for a few cases is that really going to work very well. We could use substitution, or we could use the elimination method. Now, substitution method, what you want to look for when you're using substitution is it easy to solve for one of the variables so that we can plug in the other equation? Well, this y is sitting here all by itself. We can create equation 3 and say that's y equals negative 2x plus 1, just solving this equation for y. Okay, so now we have 3x plus 2y equals 0, and we know that y equals negative 2x plus 1. So we could say, well, we're asked to solve. We're not asked, is this a correct point on those two lines where they cross? We're asked to say, where do they cross? So we could substitute this value in for y up here and say 3x plus 2 times the substitute when we put in y, negative 2x plus 1 equals 4. So 3x and then minus 4x plus 2 equals 4. If I've done my arithmetic right here, negative x equals 4 minus 2, which is 2, or x equals negative 2. Everybody okay on what we did there? So now we have solved for x, but we need to solve for y as well. So if we put in a negative here in one of these equations where we have y, we could say y equals negative 2 times the x value, which is negative 2, plus 1. Minus minus is a plus, so that's 4 plus 1 is 5. So now we're saying a solution would be, here's our solution set, negative 2 and 5. And we could say, there's our solution set. And we could even check the solution. Maybe we ought to do that from time to time, and you might be asked to check your solution. And so you might say, well, let's substitute these values in one of the equations above. Well, one of the equations was 3x plus 2y equals 4. So here's the x value and here's the y value. So 3 times -2 plus 2 times 5 equals 4. So this is a -6 plus 10 equals 4. 6 from 10 is 4 equals 4, and that's true, isn't it? So we've gone through and done a solution, come up with the answer for the solution, and then come back and check our solution by plugging these values back in, and we got a true statement. So we said, okay, looks like that's true. Questions? Okay. How about a problem might look like, let's call this problem 3, and let's say we have 4x plus 5y equals 3 and 2x minus 3y equals 7. And say you're asked to solve by using elimination, or some call it addition method. So when we're solving by addition or elimination, we're going to have a different approach. Now, if I ask you to solve this by substitution, you'd say, well, I'd have to solve for x or y here and substitute back in here, or solve for x and y here and substitute it back in up here. And that's a legitimate method that could be done. This is another method. So here, if we're asked to solve by the addition method, the object here is to see if we can combine these two equations and eliminate a variable. That's what we're trying to do. And we say, well, if I multiply this second equation by 2, I would end up with the same leading value here, wouldn't I? I could multiply the equations. I could multiply this equation by 3 and this equation by 5, and I could eliminate the y variable, couldn't I? So more than one way to solve the problem, and you have to decide which way is best for you. So let's say I want to multiply this equation, and I'm going to call this, let's call this row 1, and let's call this row 2, and let's call the next one row 3, and I'll just give it the initial R for row. And I say, well, if I multiply row 2 by 2 to get row 3, so 2 times this is 4x minus 2 times this is 6y equals 2 times this is 14. And then I want to see if I can eliminate a variable. So if I subtracted row 3 from row 1, so if I take row 1 and subtract row 3 to get row 4. So here's row 1, here's row 3, and I'm going to subtract it. So I'm going to change these signs to show that I'm subtracting. Now when I combine row 1 and row 3, the x values go away, don't they? There's none left. And the y values, I've got a 5 and a 6, and they're both positive, so that's plus 11y equals, and I've got 3 from 14, that looks like a negative 11. Okay, if I've done my arithmetic properly. So if that's the case, then I can divide through by 11. I get y equals negative 1. And then we're not done yet, right? We have to solve for both. When I say solve, we're solving for both x and y. So if y equals negative 1, we could pick any of these equations and solve for the other value. We could pick row 1, and we could say, well, row 1 is 4x plus 5 times y, which is -1, equals 3. So 4x minus 5 equals 3. 4x equals 5 plus 3, or 8, and x equals 2. All right, so now we have the value for y and the value for x, and we can say then our solution set looks like 2 for the x value and -11 for the y value, and that's our solution set. And then we can go back and check, can't we? So if we went back to check, we could just substitute these values in, which is let's take row 2. So we'll call it a check. Take row 2 and say 2 times 2 minus 3 times -11 equals 7. Okay. So let's see here. 2, where am I here? 2 times 2 minus 3 times. Oh, you guys have to catch me. Y isn't 11, it's 1. If I'm writing down the wrong values here, you guys have to stop me. So that's 1, right? Y equals -1. So 2 times 2 minus 3 times 1. So let's see, 2 times 2 is 4. Negative times a negative is a positive. 3 times 1 is 3. 4 plus 3 is 7 equals 7, and that's true, isn't it? Okay. So we've done the solution here by addition, and we have found that the x value is 2, the y value is -1, and then we put in our insert these back into the original equation, substitute back. Okay. Questions? You guys are awfully quiet today.
Could you try doing this whole like elimination addition like method again? I don't really get it.
Oh, you don't see what's happening here?
Yeah, I'm not thinking as fast as the other one.
Okay. If we're doing, let me just go through this again then. In fact, what I'm going to do is I'm going to call this row 1 or equation 1, 4x plus 5y equals 3. And row 2, the equation was 2x minus 3y equals 7. So here are the two equations that make up our system of equations. And the object is we want to see if we can eliminate a variable. Last time we eliminated x. I could go through and do that again, or I could try and eliminate the y. What would you prefer? Anybody? Guys are
Does it
quiet.
matter which one you remove first, or?
It shouldn't. It shouldn't. But just to make it easy, we'll do what we did before. So we'll say, okay, I had two equations, this one and this one. And I'm going to create a third equation by multiplying the second equation times 2. And because this is used enough, they've actually decided that if I'm going to call this row 1, row 2, row 3, what I'm going to do is I'm going to create row 3, and I'm going to say row 3 is going to be equal to row 2 times, I could say -2 this time, for instance. So I'm going to create row 3 down here by multiplying row 2 by -2. So when I do that, I get -4x, and here is +6y, and here is -14. Haven't changed the equation because I multiplied everything through. Just like when we simplify, we divide through and reduce things. Here we're just multiplying through to change what the leading values are here. Now, once I've got this, I can say, well, you know what? I can combine equations 1 and 3. I can add row 1 and row 3. and I can call that row 4. And I come down here and I say, row 4 equals row 1 plus row 2. So let's just do that. 4x minus 4x. So there are no x values here. This becomes blank. And then 5 and 6, well, that's 11 of the y values. And then 14 and 3, this is negative, that's positive, so that gives me 11, and that's negative. And then dividing through by 11, I get y equals -1. Okay, so I eliminated the x variable, solved for y, which is what I did up here. So I know what the y value is. Now I can just substitute this y equals -1 into one of these equations. So if I say equation 2 and I say 2x not equals, but -3 and y is -1 equals 7. So I've got 2x is what I'm looking for, minus 3 times y, which I've just solved for. So 2x, this is going to be a plus 3 equals 7. And 2x equals 7 minus 3, which is a 4. Divide through by 2, and I get x equals 2. So I'm saying x, my solution set, would be x is 2, y is -1, which is what I got up here. That makes sense?
Yeah, it makes a bit more sense. Thank you.
Okay, and we'll call this then our solution set. And we're kind of going through a procedure where we have some nomenclature that we're introducing by labeling the rows, so that when we do the manipulation on the rows, whether we're adding, subtracting, multiplying, dividing, whatever we're doing to these rows, we know which row we're working on. We're working on row 1, row 2. I created row 3. I did something to create row 4. I added row 1 and row 2 to get row 4. So when I do that, I'm able to then eliminate the variable x, and I'm now solve for y, and then I can substitute y back in one of the equations above and solve for x. So that's generally the procedure that's used when we have a system of equations and we want to solve by eliminating. Here we eliminated x. We did some manipulation on these rows to eliminate the x value. Okay, questions? Okay, let's try another one. Let's say I have, well, let's 9 plus 3y minus 2x equals 0. And let's say 8 minus 3x minus 4y equals 0. And we want to solve for x and y. Well, you notice I haven't put these in a nice order. I'm going to have to kind of rewrite these like we had the above equations so that we can solve them a little more easily. So let's put them in the order that we traditionally put them in. And we could say, of the form ax plus by equals c type thing. And if we want x's to be positive, I could say, well, this could look like 2x and minus 3y equals 9. I could take this equation and rewrite it to look like this. Make this to the other side, bring y to the other side, and leave 9 where it is. So this could be my first equation that's been rewritten. And I won't give it a row number yet because I'm not really working on it. I'm just rewriting the equation. And similarly, I want to rewrite this one. So if I make it x is positive, I could say, well, that could be 3x plus 4y bringing this to the other side, bringing this to the other side, and leaving 8 where it is. So now I've got 2 equations, and I might call this row 1 and row 2 for my equations. And now I've got the equations set up where I want to be able to solve for them. And I did this by rewriting the equations into this format, ax plus by equals c. So now I've got the rewritten equations. They look like this. And now I want to use a method. I could solve these for y and graph them and see if I could come up with a value. Probably not going to be too successful. I could eliminate a variable. Well, that could work. Or I could, graphing didn't work, but substitution could work. I could solve one of these for x and substitute in, or solve one of them for y, substitute back in. That's a possibility. And we did that earlier. But this time I'm going to, again, solve it using addition or elimination. So in order to do that, I'm going to have to get the leading value here to be the same so that I can subtract and get rid of that variable, either x or y. And we want to do it the easiest way we can. And we could say, well, I've got 2 of these and 3 of these. So I could multiply this by 3 and this by 2, and we could combine and get rid of the x's. We could multiply this by 4 and this by 3, use that to get rid of the y's. Which way would you guys prefer? How about a new volunteer? Any new volunteers with ideas on what we might want to do to eliminate these variables, either x or y? Either way should work. Well, maybe we'll do it both ways. Should we do it both ways? Let's try and eliminate x and see if that works. So if we multiply row, I want to create row 4. And I'm going to say row 4 is going to be row 1 times 3, and row 5 is going to be row 2 times 2. So that should give me a 6 as a leading value here, shouldn't it? So row 1 by 3 should give me 6x minus 9y equals 27. And row 2 by 2 should give me 6x plus 8y equals 16. Everybody agree? And then we're going to want to eliminate the x variable because that's all we multiplied. To eliminate that, so I'm going to subtract. So I'm going to make that a negative, that a negative, that a negative. We'll change the signs. The x's go away, and row 6 now contains -8, -9. That's 9 8 is 17, y equals, and then 16 from 27 looks like that's going to be 11, doesn't it? So if that's 11, we divide through by the -17, y equals 11 over -17, and we've now solved for y. Okay, y equals -17. And then we want to be able to go back and solve for x. Okay, so if we want to solve for x, we could substitute y in one of the above equations. So if we take row 1, that was 2x equals, and not 2x equals, 2x minus 3y, and y is 11 over -17, and that's equal to 9. And we want to solve that for x. Okay. Go ahead and solve that for x. Let's see if we can all agree what x is equal to when we solve this equation here for x. So keep in mind, we're not doing anything except solving one equation, one unknown, but it's got a fraction in it. But we have to be able to do this in order to solve the system of equations using the addition or elimination method. So let's go ahead and do that and tell me what you get. 334. Let's see how long it takes us to solve that. And we can have a new volunteer, or I can call on somebody if that's a preferred method. Either way works for me. So what you guys get for X?
Yes.
Okay, everybody with us now on how we solve for, first we solve for Y, then we solve for X. We solve for Y by multiplying row 1 by 3 and row 2 by 2. That gave us a leading value of 6 for both those equations. Subtracted one from the other, we eliminated a variable, solved for Y, then back substituted in. Okay, questions on what we did there at all? Rather than take the time to go through it a different approach, we'll end up with the same answer, but we could also have eliminated the X values if we want, or the Y values if we wanted to. All right, let's try a new one. Let's see here. We're up to problem 5. Let's say that 5 looks like the following. Let's put it in order. 5x minus 2y equals 4, and negative 10x plus 4y equals 7. And asked to solve. Now you could be asked to solve and not told the method. You know, you could solve it graphically or by substitution or addition elimination. Since we're working on addition elimination right now, let's just go ahead and solve this by elimination, sometimes called addition. So here's row 1, row 2. And anybody have any suggestions on which one you'd like to remove?
I think we can remove both by just, oh wait, never mind. Oh wait, actually if we do the top row, we can remove both X and Y if we multiply by 2.
All right, so we'll take this, we'll call row 3 equals row 1 times 2. Is that what we want to do?
Yeah.
Okay, so multiply row 1 times 2, we get 10x minus 4y equals 8. So now we've got a row 3 here. Okay. All right,
If we use elimination with row 2, we'll get rid of both X and Y.
All right, so we're just going to add these together.
Yeah.
Row 4 equals no X, so we get a 0 here. And we get a 0 here, and we get a 15 here. Okay. What do we think's going on here? Is this true or false? New volunteer.
That's
Is this
false.
okay? That's going to be false, isn't it? So if this is false, this isn't a solution, is it? 0 doesn't equal 15. That's false. So that indicates that we don't have a solution set here. We eliminated variables and they all went away. So we can say then the solution set in this case is the empty set. It's 0. And we might want to figure out maybe why that's the case. So if we were to go back up, well, I'm going to leave that for, rather than take the time right now to do it, I've got other examples I want to take you through. But if we solve both of these equations for y, we might find out why this is an empty set. And keep in mind that if these equations were parallel, they wouldn't cross anywhere, would they? And so we'd have an empty set. So it's possible then that maybe these equations are parallel. That is to say, m1 equals m2. The slope of equation 1 is equal to the slope of equation 2. Okay, good. All right, let's try a different concept here. Let's say we have a situation where we're talking about mixtures and quantities and things like that. And let's say we have a chemist. Some of you might be going into chemistry. And you might need to mix an 18% acid solution with a 45% acid solution. Maybe that's solution 1 and maybe this is solution 2. To obtain say you want to obtain say you were given this and this creates 12 liters, let's say, of a 36% solution. So that's solution 3. So we might say, we don't know what the quantities are. You might be asked to find how many liters of each must be used. So you're asking for maybe the quantity here, maybe I'll call that Q1, and the quantity here, maybe I'll call that Q2. And that gives me a quantity here of 12 liters. So if I put that in equation form, it might look like 18% of some quantity 1 plus 45% of some quantity 2 is going to give me 12 liters of a 36% solution. Might look something like that. And if that's the case, then I have to decide, well, what do I want to use here? Let's see here, do I have any suggestions here on what I might do to solve this? Instead of calling this Q1, I might want to call this, I could call it Q1, I might call it X. Maybe I'll call this Y. And remember, X and Y are the quantities, aren't they? So if I'm looking at quantities, I've got this equation, which relates an 18% solution, this much of it, and this much of a 45% solution. And that gives me 12 quantity. In this case, I said liters of a 36% solution. And we look at that and we say, well, that's fine, but this is one equation maybe I'll call this equation 1, but I have two variables, x and y, so I need another equation. So I'm going to be unable to solve this unless I can develop a second equation out of the information that's given, which is this information here. Can you think of another equation that we could develop based on what we're given? Well, this is a quantity. This is a quantity. This is a quantity, isn't it? So that tells me that x, the unknown quantity, that value, plus y, that unknown quantity, is going to be give me 12. I said this was liters, so I'll call these all liters. So I know that this percent times this amount plus this percent times this amount gives me this percent of this amount. So the amounts have to add up, don't they? So now I have two equations. And the question is, am I able to solve those two equations? And how would I do that? Well, this looks like it's set up nicely to use substitution, isn't it? So if I've got equation 1, equation 2, and I've got x plus y, well, I could solve this for y. I could say y equals 12 minus x, and then solve by substitution. Couldn't I do that? Just substitute back in. So if I go up here and I could say 18%, well, when I'm using that in equations, 18% becomes 0.18, doesn't it? 0.18x for this part plus 0.45y. I can put y, but I've said that y is the same as 12 minus x. And that equals 12 times 0.36. Okay. So if we were to solve this, is this an equation you could solve? One variable, one equation. So go ahead and solve this. And let's see if we agree on a value here. So if I combine this 0.45 and this 18, looks like I get negative 0.17. Is that what you guys get? I guess that's negative 27. That's 17, so that's going to be 27, isn't it? That's an x, but by combining those two, bringing the 5 to the other side, it becomes a negative 5.4. So negative 5.4. To that I add 4.32. And it looks like I get a negative 1.08 if my arithmetic is correct. Okay, and then we're solving for x. They're both negative, so I can just make that a positive. X equals 1.08 divided by 27. It looks like that becomes 4. So x is 4, and the units are what? Liters. Okay. if that's the case, and then I want to solve for y, well, up here I had y equals, and if I solve this for y, I'll get 12 minus x, which is 12 minus 4, which is 8. So it looks like y equals 8 liters. Okay. So it looks like then that the chemist mixes 18% solution. So he wants 4 liters of the 18% solution and 8 liters of the 45% solution to get 12 liters of the 36% solution. Okay, makes sense to everybody? Questions?
I was confused on how you got the second equation, x plus y equals 12.
Okay, what we're doing is combining quantities. So this is a percent times a quantity, percent times a quantity, percent times a quantity. So this quantity plus this quantity equals this quantity. X plus y equals 12, and the quantity given was in liters. So we're saying we have now 2 equations, one involving percent and quantity, and the other involving just quantity.
But how do we know that x plus y equals 12?
Because this is a quantity, this is a quantity, and this is a quantity. This is a percent. Doesn't affect quantity, it affects the type. So you could call this a type if you want. And this is the amount of this type. This is the amount of this type. Gives me this amount of this type.
Okay, got it. Thank you.
Other questions?
I got 4.5 for x rather than 4.
All right. So when you did your equation here, are these the values that you use? 0.18x plus 5.4 minus 4.5x equals 4.32. Apparently you had some,
Yes.
well, then you must have an arithmetic situation then. When you combine negative 0.45 and positive 0.18, did you get 0.27?
Yeah, I got negative 0.27.
Negative 0.27. Okay, that's fine. And then on the right-hand side, you combine the negative 5.4 and the positive 4.32, and you got a negative 1.08.
Yes.
All right, so then you divide 1.08 divided by 0.27, and what did you get?
The 4.5. Let me divide it again.
I don't think you get 4.5. $27 times 2 is 54, and 54 times 2 is 108. So we know that the answer is 4, don't we? Not 4.5. Other questions? Other questions? We can see that it's important then that we do our arithmetic calculations on our calculator have to be accurate as well, not only setting up the equations, but we have to be able to do the arithmetic. Okay. One last problem, and then we'll take a break and we'll come into the next section. This next problem has to do with, well, let's see, which one should we do? We've got, well, let's do the one. Let's say we have a boat on a river, and we have the, and we're trying to find, let's say we have some boat here that's going down this river, and it's going in this direction, and maybe the river is going in this direction. So I might want to call that the water is going that way, and the boat is going that way. And in this problem, what we're going to do is we're going to say that this boat can travels, let's say 84 miles in 2 hours with the current. So, so I'll set up, let me set up two situations. Here's the boat. Well, let's say the water's this way and I have the boat going this way with the current. And then I'm going to give you a situation where the boat's going against the current. And what we're going to want to try and find out is the rate of the current of the water and the rate of the boat. And the idea is if the boat travels, let's say 84 miles in 2 hours with the current, and against the current to do that same 84 miles takes 3 hours against the current. So the boat travels 84 miles in 2 hours with the current and travels 84 miles in 3 hours against the current. So here it takes 3 hours. Here it takes 2 hours. This is a problem of distance equals rate times time. So that's what we're going to use to solve this problem. Distance equals rate times time. And sometimes it works to set up kind of a table. And we might say, maybe this is a velocity or rate. And maybe this is time, covering that. And this is distance. And we can say, well, the time is 2 hours to go the 84 miles. We're going 84 miles. We're going 84 miles in each case. Here it takes us 3 hours. Here the rate when we're going with the current. We don't know what the rate of the current is. That's this value. And let me just call that y, some value y. And the rate of the boat, I don't know what that is either, some value x. So if we're going with the current, then we can say x plus y, this rate of the boat and the current. So here's boat and current. In 2 hours, I can cover 84 miles. Distance equals rate times time. So rate times this rate here times time is going to give us 2 times this value here. So that 84 equals x plus y. So with the current. And then against the current, I'm going to be going boat and current here. Takes me 3 hours. So here I'm going to say it takes 3 hours to go x minus y, same distance. Okay, so now I have two equations here and two unknowns, the value x and the value y. So let me set up my two equations. So I can distribute this x and I can say 2x plus 2y equals 84. And 3x minus 3y equals 84. And now I want to solve this system of equations. So we're given the initial situation. From the initial situation, we develop a table using distance equals rate times time. If the rate is 50 miles per hour and we travel for 1 hour, we're going to go a distance of 50 miles, aren't we? So similarly, the rate of the water, current, and the boat, we don't know, but when they're added together, it takes us 2 hours to go this distance. And when they're subtracted, it takes 3 hours to go the same distance. So we end up with these two equations. Okay. So we might want to say, well, then, is there a way we can reduce that? That is to say, simplify, or do we just want to solve it the way it is? Which we can. There are always multiple ways to solve problems. So in this case, if I divided Well, let's not even do the division. Let's let you choose however you want to do it. How would you like to solve this equation? You know, we could solve for y and substitute. We could eliminate one of the variables. I guess it would be easy to turn this into, if we divided this equation through by 2, we could have what? X plus y equals 42. And if we divide this equation by 3, we have x minus y equals 84 over 3, which is 28. We've simplified. This isn't the way you have to do it, but that is a way. We could simplify it that way. Now, if we simply add these two equations, we're going to eliminate the y, aren't we? So we'll say 2x equals 8 and 2 is 10, carry 1. Looks like 2x is 70, or x equals 35. And we said this was miles per hour from the above units. So we solve for x, and then solving for y, I guess we could substitute x here. We could say 35 plus y equals 42. Y equals 42 minus 35. Y equals 7. And that's miles per hour. So we've taken the given information, created a table using distance equals rate times time, substituted in the values, created the system of equations, solved that system of equations after simplifying, eliminating the y variable, solving for x, then back substitution to solve for y. That work for everybody? Let's take our break. We'll take questions after the break. Is 5 minutes enough for a break for everybody?
Yeah, that works.
Okay, we'll see you guys in 5 with your questions. Okay, are there any questions? If there are no questions, why don't we go on to the next section?
I had a question.
Go right ahead.
What were we trying to find in the last problem? The rate?
What are we trying to find? What do these variables represent? Is that your question?
So, like, what was the problem asking for? Was it asking for the x and y values or the rate?
Here we have rate, and here we have x and y values. Distance equals rate times time, and the rate is given in terms of x and y.
So my question was, what are we looking for?
We're looking to solve for x and y.
Okay.
And here we've labeled x as the rate of the boat and y as the rate of the water.
Okay, thank you.
Other questions? Okay. Let's go to the next section and make sure I get everything there. If there are time left, we can come back and go through some other problems, but let's just make sure that we get through everything we're supposed to get through. So 7.2 talks about systems of linear equations in 3 variables. Very similar to what we've done, but we're going to look at solving for 3 variables. It just makes it a little more interesting. So let's take a look here, get some paper out here. And we'll use the same kind of approach you used before, which was to show, for instance, if I'm given a system of equations and I'll put them in order. So if I say x minus 2y plus 3z equals 22, and that's equation 1. And maybe equation 2 is 2x minus 3y minus z equals 5. And equation 3 says 3x plus y minus 5z equals negative 32. So that's what we're given. And we might be asked, is the point -1, -4, 5 a solution? And how would we show whether that's a solution or not? We could substitute in, couldn't we? So here's x, here's y, here's z. So let's just try equation 1. And in equation 1, we put -1 minus 2 times y, -4, plus 3 times z, which is 5, and that's supposed to equal 22, and we're going to say true or false. So -1, +8, +15 equals 22. 15 and 8, that would be 23, wouldn't it? 8 and 5 is 13, minus 1, so that says 22 equals 22. So that's true, isn't it? So it looks like that if we use those solutions that are provided and put them into equation 1, we get that they're true. Why don't you substitute them into 2 and 3 and tell me if you think they're true for 2 and 3 as well. And just turn on your mic and let's have some new volunteers, some new participants. Or I can call on people if we have silence, I can just call on some people. That works too. Either way works.
I think it works. I mean, sorry, I think it doesn't work.
Alan, what do you think?
I'm currently still solving, Professor.
Okay, no problem. You guys get true for the second one?
Yeah, I did.
Okay, good. And the third one, let's see, -3, -4, -25, -3. Is that going to be right? -32. 4 and 3 is 7. Yeah, 7. -32, -32. So it looks like that's true as well. Did you guys get true for the third one as well?
Yeah.
Okay, good. All right. So we could be given 3 equations. We could be given a solution to the 3 equations, and we could verify whether the solution is correct by simply plugging that value in. Okay, good. All right, let's try a different one. Let's say we're given system of 3 equations. X plus 4y minus z equals 20, and 3x plus 2y plus z equals 8. And let's say 2x, let's say a minus 3y plus 2z equals, say, -16. And we're asked to solve for that one. So now we're going to have to do some manipulation on these rows. So now I'm going to come back and call them row 1 and row 2 and row 3. I'm labeling them because I'm going to do some multiplication and addition and what have you, subtraction, and I want to be able to determine which row I'm talking about. So the idea is I want to see if I can eliminate a variable. And I look up here and I see, you know what, I've just got one of the z's and one of the z's here. So I could add row 1 plus row 2 to generate, I've already got row 3, so let's call it row 4. I'm going to generate a new row. And I'm going to say row 4 is equal to row 1 plus row 2. So let's just do that. If I add row 1 and row 2, I get 4 of the x's and 6 of the y's. The z's are eliminated. We have a positive and negative, and that's equal to, looks like 28. Okay. So that gives me a new row with just 2 values in it. Now I'm looking to see if I can eliminate, let's see, can I take these 2 and eliminate, let's see, well, I guess I could eliminate a z if I took row 2. So let's say row 5 equals row 2. And what can we do? Multiply it by 2. So let's say 2 times row 2, 2 times this, plus row 3. So let's just do that. We're going to get a new row 5. I'm going to say 2 row 2. So 2 row 2 gives me a 6x plus 4y plus 2z equals 16. And we're going to add it to row 3. Row 3 says 2x minus 3y plus 2z equals negative 16. And I wanted to eliminate this z, so I'm going to have to subtract. So I'm going to put a negative here, positive here, negative here, positive here, and combine those. So row 5 becomes, if my arithmetic is correct here, 4x plus 7y. The z's cancel, and that equals 32. And I'm going to call that my row 5. I'll relabel it here. Okay, so now I have x's and y's and like that. So that looks pretty good. So I've got, looks like I could combine row 4, which has 4 of the x's, and row 5, which has 4 of the x's. It looks like I could say row 6, and row 6 is what I get when I take, let's take row 4 minus row 5. So 4 minus 4, the x's go away, and the y's become 6 and 3. That's 9y. Z's are gone, and so I get 32. And what do I have here? 16 and 28. Looks like that's 48. Is that what you guys get? My arithmetic is correct here. So y equals, I don't think my arithmetic is right here. I did something wrong. 4x. Let me redo that. I had x 20. If I take, yeah, I took the first one, and that was good. 4x, 6y, 4x, 6y, 28. That looks good. This is a good one. All my calculations are correct there. And then if I take 2 and 3 and I want to eliminate the z, 2 and 3, eliminate the z, and it looks like I get 4x, 7y, 32, y equals, looks like I did something, 7, 4x minus 7y is 32, 7y. If we add those together, well, let's see, that's gonna go away, and I'll get 7 and 6. I think these signs, somehow these signs got backwards here. 7. Oh, this is a negative here, isn't it? So times 3, this is supposed to be, that's supposed to be a negative, isn't it? You guys got to catch me on these signs. That's supposed to be a negative 3. Okay, so this would give me not negative y, not negative 9, but negative, is that 8? Let's see, 9, 12, 7. What am I doing here? 28. That's good. That one is good. This is 4x, 7y, 32. These signs, what am I doing with these signs here? I think if I want that to be a negative, and this is a negative, and this is a negative, and if I combine those, if I combine, then I get negative, not this. You guys got to watch me on doing these arithmetic calculations here. So let me just rewrite this. So I'm combining 4x plus 6y, that's 28. We know that's good. And then I'm going to combine that with down here, negative 4x, negative 7y, and a negative 32. That's this thing here. So when I combine those, 4 and 4, that's going to be 0. 6, I have a negative y, and combine 8, 32, that's going to be 4, negative 4, sorry, or y equals 4. So that's good. So I was able to eliminate everything except y from this second set here. Now I've got y equals 4, and I can substitute back in, can't I? So if I take this equation and substitute y is equal to 4, I'll get 4x plus 6 times 4 equals 28. 4x equals 28 minus 24, which is 4, and x equals just 1. So I've got y is 4, x is 1. And now I need to solve for the last variable by substituting back in. And if I take equation 2, which is 3x, I could take any of the equations I want, plus 2y plus z equals 8. If I let y equals 4, 2 times 4 plus z equals 8, and 3 times x, which is 3, that tells me that 3 plus 8 plus z equals 8. Those 8s are going to cancel, and z is going to be negative 3. So going through that process of elimination, I ended up with a solution set of putting them in the order of x, y, and z. 1, y is 4, z is negative 3. So that's the solution set I get on that. Questions on what we did there, or in the nomenclature or anything? Started up here. And the key is making sure that you label the equations as you develop them, and you're trying to eliminate a variable as you go through here. And we found that we just took a look at equations 1 and 2 and said, well, I can easily eliminate the z by just combining 1 and 2. And I called it 4 and put it here. So I said, that's equation 4, 4x plus 6y equals 28, which I was able to use later. So that's good. And then I said, let's combine 2 and 3 and eliminate z and call it row 5. So I said that here. So I said row 5 is going to be equal to 2 times row 2, which is this value here, plus row 3. Okay, so when I multiplied this by 2, I ended up with 6, 4, 2z, 16. Okay, and then when I subtracted, I ended up with the value that I used down here. So 4x minus 7y minus 32. And when I combined those, we eliminated the x value, got y as 4. Okay, so if we carefully move through labeling each of our rows, what we're calling them, you could call them equations or rows, whatever you prefer. We call them rows because later on we're going to develop some matrices. And in the matrices, which look like this, maybe that's a 3 by 3 matrix, and we call these rows, and we call these columns. And so we end up putting these equations into these rows. And so we'll have rows and columns. So I end up calling these guys rows because we're kind of anticipating what we're going to see in the future. Okay. If there aren't any questions, I will go on to another example. I'm going to call that problem 2. Let's take a look at another problem, which I'll call problem 3. And let's say I'm given the following set of equations. And again, row 1, row 2, row 3, And maybe we have 2y minus z equals 7. I might have x plus 2y plus z equals 17. I might have 2x minus 3y plus 2z equals -1. And I say, well, let's see. Can I eliminate anything here? And what would be easy to eliminate as I go through here? So I guess I could eliminate x and z from equation 2, x from equation 2 and 3. Here's 2, here's 3. So if I combine these two guys, you notice I have one x that's positive, one z that's positive. Here I have two x's and two z's, and those are both positive. So it looks like I could combine those by multiplying this equation. So let's develop another equation by taking row 2 times -2. So if I multiply row 2 by -2 and call that row 4, maybe here's row 4 here. So row 2 times -2 gives me a -2x. Positive, no, that's going to be negative again, isn't it? Negative times 2 is -4y. And -2z equals -34. So 1, 2, 3. I created equation 4 by doing this multiply. And now I'm going to create equation 5 by combining those two equations. So if equation 5 is equal to row 3 plus row 4, I'm just going to add these. So we're going to have 0 x's minus 7y plus 0 z's equals, and I'm just adding, so I'm going to get -35. And I could call this row 6 if I want to, and say 7, divide each of these by -7, and I'll get y equals 5, won't I? Okay, and I'm going to stop right there and make sure that everybody agrees on what we did, why we did it, and how we did it.
Could you go over how like the rows came in place, like how you thought like row 4 and beyond?
Yes. So up here we said we're going to multiply row 2 by -2, and that's going to create row 4. And row 4 is here. So when I multiply -2 times x, I get -2x. -2 times +2y, and I get -4y. And -2 times +z, and I get -2z. And -2 times 17 gives me -34. So that's row 4. Then I said, what if I combine row 3 and row 4? That is to say, I add them together. X's are going to cancel because we have a +2 and a -2. Z's are going to cancel. I have a +2 and a -2. And so the only thing left are the y's, which are -4 and 3, 7, and -34, -1 is -35. So 7 into 35 goes 5 times. So we have y equals 5 as one of our solutions. Now we look above and we say, well, using y equals 5, can we use that to solve any of the other variables? Well, I know y, I know that value, which means I should be able to solve for z. So I can say, and if I want to put it in row form, there's 7. So I could say 2 times 5 minus z equals 7, or z equals 10 minus 7 or 3. So substituting back into this equation, I solve and say z equals 3. And so now I've got both y and z. I just need to solve for x. So equation 2 I could use. Remember equation 2, which is row 2 up here, look like x plus 2y plus z equals 17. We're going to solve for x. I have y and I have z. So x plus 2 times y, which is 5, plus z, and I just have 1z. So that's going to be 3 equals 17. X plus, this is 10 and that's 3, that's 13. 17 or x equals 17 minus 13, which is just going to be 4. So we started off with 3 equations listed here. We multiplied equation 2 by -2 to get equation 4. Added equation 4 to equation 3. Now that eliminated all the variables except y, so we were able to solve for y. Then we looked above and said, if we substitute 5 for y in equation 1, I can solve directly for z. That's what I did. So when I solved for z by substituting 5 for y, I got z equals 10 minus 7, move the z to the other side, move the 7 to the other side. Z is 3. And similarly, we solve for x in equation 2. Okay, we could use equation 3 if we wanted to. They all should work. Okay, so the solution set that we come up with then is x is 4, y is 5, and z was 3. So here's our solution set here, 4, 5, and 3 for x, y, and z. Questions? Okay, let's see here. What would be another interesting one here so you don't get too bored? Let's try, let's say, well, let's work one that looks like this. This is good. Let's call this problem 4. Let's say we're given an equation that looks like y equals ax squared plus bx plus c. That's what we're given.
Could you please move the paper down, please? Perfect.
Yeah.
Thank you.
And let's say that this graph, this quadratic function, is going to be some sort of a parabola opening, depending on whether this is positive or negative. This is going to be a parabola, isn't it? And so let's say that it passes through the following points. Let's say it passes through 1 and 4. That's x and y. And it passes through 2 and 1. And it passes through 3 and 4. And maybe you can see where I'm going with this. So we've got 3 points. And we want to see if we can come up with an equation. The object of this game is to plug in the values for A, B, and C. So really this is saying find A, B, C in this equation here. Okay. So if that's what we're given and that's what we're asked to find, let's see how we can progress. So let's take the first point, x and y. So instead of saying y equals ax squared plus bx plus c, and y is 4. That's this y here, isn't it? So equation 1, 4 equals a times x, which is 1, squared, plus b times x, which is 1, plus c. So here we have an equation, one equation. Okay, everybody see how we got that? So we have 4 equals what? A plus b plus c. So that's an equation. And again, we're trying to solve for these 3. Okay, now how about we substitute the second point? So the second point is 2 and 1. So I have, for the second equation, I might say here's y, that's 1, equals, substitute 2 for x. So it's going to be a, x is 2, quantity square, plus b times x, which is 2, plus c. Or the second equation then would become 1 equals 2 times 2 is 4a plus 2b plus c. So here's the second equation. And now we need the third equation. So we use the points 3 and 4. So here we say 4, the y value, equals a times x. And x is going to be what?
3.
3. And we're going to square that, plus, and then we have b, and we have 3 of those, so I'll put 3b, plus c. So 4 equals 3 times 3 is 9a plus 3b plus c. So you'll notice then that this gives us 3 equations with 3 unknowns, a 3 by 3 matrix. And we were given this in a different way. We were saying we have an equation y equals ax squared plus bx plus c, and we're given 3 solutions. That is to say, it passes through these 3 points. So we substituted x and y and developed 3 equations. Okay, so now we want to solve these just like we did before. Are we able to somehow eliminate A, B, or C as we go through here? Okay, so can we eliminate C from equations 1 and 2? Here's equations 1 and 2. This has a C out here. This has a C out here. So if we multiply equation 2 by, or just subtract it, either way we want to look at it, we could develop, if I call this again, row, I'm going to call them row 1, row 2, row 3 instead of equation 1, 2, and 3, because we're going to later put them into a matrix terms, which would be rows and columns. So let's say we develop a row 4 equation, the fourth equation. And we do that by combining, we say row 4 equals what, maybe we take row 2, let's say row 1 plus row 2 times -1. And what does that give us? Row 2 times -1, and add that to row 1. Well, row 1 was 4 equals A plus B plus C, and -2 times row 2, so -2, so that'd be -2 equals -8A, and then times row 2, -2 be -4B, and then -2 and I'm combining that with the C row. So let me get my terms right here. So what we want to do is eliminate C by combining those. Go
Mr.
ahead.
Lombardo, are
Go ahead.
we multiplying it by -1 or -2 for row 4?
Well, let's take a look here. Row 1 or 2 by negative. What are we trying to eliminate? Trying to eliminate C. We better multiply by -1, huh? By -1, yes, by that value there. So 2 times -1, we're going to get, let's change these values to what they should be. So good catch, and you want to make sure that we're being honest as we go through here. So row 1 is 4 ABC, and we're just going to negative row 2. So we're going to get a -1, -1, -4, -2, and negative C. So let's see what we get when we combine those. The object is we want to eliminate C, wasn't it? So when we did that, it looks like we got 3 equals -3A -B. Okay, did we do everything correctly there? Okay, so now we've got a row that has just these values in it, and that's what we're calling row 4. So let's say row 4 equals this thing here. 3 equals -3A -B. Everybody agree? We all okay there? And the object is, we want to develop 2 equations that have just A and B. So we eliminated C by combining row 1 and 2. Let's eliminate C from row 2 and 3. So we're going to do that. So row 2 look like row 2, row 3. And what are we going to have to do? We're going to have to subtract again, aren't we? Okay. So let's multiply row 3 by negative, combine it with 2. So here we have 2, and I'll say that. So 1 equals 4A plus 2B plus C. In row 3, we're going to do a negative, so it's going to be -4 equals -9A, -3B, -C. And when we combine those, we get -5. And here we get -5A, -B, and the C's cancel. Positive and a negative. So if we've done our arithmetic properly, we should end up with a -5 equals this. So now we've got just these 2 equations, and I could call it row 5. Now I want to combine row 4 and row 5 and see if I can eliminate a variable. So here's row 4 and 5, and it looks like I've got a B over here that could go away by multiplying this by -1, couldn't I? So I could say this becomes +5 equals 5A plus B. Maybe I call that row 6. And I'm going to combine that with row 4, which is 3 equals -3A minus B. We did that so that we could eliminate the B's. So combining those, 8 equals 5 minus 3, 2A, or A equals 4. Is that what we want to do here? Looks like that's what it comes out to be. Okay, so in doing, as we go through this, and you can check my addition and subtraction and so forth, but it looks like then we ended up with 3A. Well, let me just go through just to make sure. We got row 4, we said was 3 equals 3A minus B. That's good. And row 5, we said there was 5. Row 1, 2 is 1. This is wrong. That's not a negative. That's an equals. That's a positive one, isn't it? Because row 2 is a positive one. So this becomes a 3. Got to be very careful as you go through this. So if we combine 4 and 5, that's a 3. So combine that becomes, looks like that's a 2. And this is a 2. And what are we combining down here? Let's make sure we get these values correct. So we combined row 4, we get 3 equals -3. That's good. So I like this one. That's good. And row 5, -3, -5. This guy, combine those, and we get 2. Let's see, 4 and 5. What are we doing here? 4 and 5, that should be the same. 3, this is 5A. I think these are positives here. Row 5. How did I get row 5 here? -3, multiply this by -1. So let's see, if we multiply that row 5 by -1, that's going to be a positive, positive, positive. So 3 equals 5. That looks better. Yes, we multiplied this -1 out here. So when we combine those, we get not 2, but this is 3 plus 3 is 6. And we combine 3 and 5 gives me a 2. 2A, 6, those cancel. So A equals 6 over 2, which is 3. Okay, so we need to be careful as we go through and create our rows. It's important that we use the notation that will help us best set up what row 4 is, what we do to row 4 to get row 5. And so if we label each of the operations that we perform on each of the rows, then we're able to follow more clearly what it is we're doing and what we're trying to eliminate. In this case, we're trying to eliminate the B value so we can solve for A. Now that we have solved for A, we can then substitute back in one of the previous equations. Okay, because we have A. So for instance, up here, let's see if we've got an equation that just has A and B. It looks like this has just A and B. So if we were to solve, substitute 3, this value here, for A in equation 4, equation 4 will look like this. So we said, if we substitute, we say 3 equals -3, and we'll substitute 3 for A minus B. So this is this. So 3, and this is 9. So that's +9 equals B equals -B. -B equals 12, or B equals -12. Okay, so now we're just going back and substituting back in the previous equations. So we solve for A by eliminating the B out of these two, solve for B, and now we just have to go back and solve for C. We can solve for C by substituting 3 for A and -12 for B in the first equation. So first equation look like 4 equals, let's see, A, which is 3. Equation 4 plus, no, equation 1. We're back up here. So we're going to solve, we're going to say 4 equals A plus B plus C. So 4 equals A plus B, which is -12, plus C. I just solve for C. Okay, so C equals 4 minus 3 plus 12. It looks like bring the 12 over, bring that over. So 12, 4, 16 minus 3 looks like that's 13. So C is 13. So now we have our solution set, which says A is 3. A is 3, B is negative 12, C is 13. Now we have to ask ourselves, and you always want to do this, at the end, when you think you're at the end, go back and read, what was the question? What are we solving for? And so we go back here to the beginning and it says, hey, we were given something that looked like ax squared plus bx plus c, and we were asked to find a, b, and c in for this equation. And we went through the process substituting the points that were given. We developed 3 equations, and then using the process of elimination, first eliminating c and then eliminating b, solve for a, and then go back and substitute in, solve for b and c. And so what were we asked to do? We were asked to find y equals ax squared plus bx plus c. And now we have the values. A is 3, so 3x squared, and then plus b, and b is negative 12x plus c, which is 13. So this tells us that the equation that we were looking for is this equation, y equals 3x squared minus 12x plus 13. And how did we find that? By using the values that were given, developing 3 equations, and then using those 3 equations, solving 3 equations and 3 unknowns for A, B, and C. Okay, I'm going to stop at that point and ask for questions. You must have some questions on what we did here. I'm guessing anyway.
So would the answer be the solution set, or would it be the equation?
Well, it would be the solution set if you were just saying what are the solutions that we solve for A, B, and C. So here's the solution set for A, B, and C. But the question said find this equation. That is to say, substitute A, B, and C that you solved for into this equation. What does this equation become? And this equation becomes 3x squared minus 12x plus 13. So we went through a lot of procedures here. If you go through them systematically and watch your pluses and minuses, you're going to find they work out fine. But it is and can be a long procedure to go through.
Thank you.
What other questions do you guys have? Now, if there aren't any other questions on 7.2, I want to go back to 7.1 and pick up that one. I thought I said I didn't do one on 7.1. Let me make sure that I cover everything. 7.1. Oh, yes. So I'm going to go back to 7.1 and work the problem that I ran out of time on, but I'm going to cover it now. We've got a few more minutes. So on this one, we have a company that's a manufacturer. And for any of you going to business school, you'll get this kind of a problem frequently. A company manufactures, for instance, some units, whatever they are. Let's say they're running shoes. And in this case, we're looking at computing the cost as a function of the number of shoes produced. And so cost as a function of X would look like the fixed cost plus the variable cost. And the variable cost is the cost per shoe. Okay, so if I say that the company manufacturing these shoes has a fixed cost of $300,000. Maybe that's plant and equipment and so forth. Huge cost to set up the factory to produce the shoes, plus a variable cost of say $30 per shoe. So if this is dollars per shoe times the number of shoes, 30x, then that's going to give us the total cost as a function of the number of shoes. So if we set up what this looks like pictorially, we're going to say, well, we've got 300,000 here is a fixed cost. And this is say the number of shoes. And this is dollars along the vertical graph. If we don't produce any shoes, if the number of shoes is 0, we're still going to have $300,000 because we had to set up this plant and equipment and all the materials it took to set this thing up. And then once we do that, we're going to have some sort of variable costs. And because this is linear, we're going to say, well, the variable cost is going to have a rate that goes up at 30 times X. For every shoe that I produce, I'm going to have a variable cost of $30. Maybe that for the leather and the rubber and the shoelaces and insignias and whatever it is that goes on that's per shoe, that amounts to cost per shoe. So then if I were to say, write a function, a cost function for producing the running shoes. So if one is produce a cost function, you would say, well, this equation is a cost function. That is to say, cost as a function of the number of shoes produced. Then you would say, well, it's going to cost me 300,000 plus 30 per shoe. So that'd be a cost function of producing X pairs of shoes. This would be fixed. That would be your variable cost. Okay. Now you might be able to say, well, how about a revenue function? Where revenue has to do with, let's say here's R for revenue as a function of the number of shoes sold. And you say, well, the number of shoes sold, well, that's X. And the revenue says, well, how much are these shoes selling for? Well, let's say the shoes sell for $80 for a pair. Then the revenue function is just going to look like $80 times however many pair I sell. If I sell 1, I'll make $80. If I sell 2, and so forth. Okay, so here's my cost function. Here's my revenue function, and you might be able to see kind of where I'm going with this. Cost function look like this. So here's C as a function of X. Here's number of shoes. So these are dollars out here. And now if I sell number of shoes, if I sell 1 shoe, I make $80. If I sell 100 shoes, I make $800. If I sell 1,000 shoes, I make $80,000. So I'm working my way up here. Okay, so I'm going to have a revenue function that's going to go up linearly as the number of shoes increases. And you can probably see that where I'm going is, where does this revenue function cross my cost function? Because that really tells me my break-even point, doesn't it? In other words, I have to sell this many shoes just to break even, just to cover my costs. My costs are this heavy 300,000 for my plant and equipment and so forth. But then I'm also have some costs that vary. For every pair of shoes I create, I'm going to have to buy the leather and so forth that goes into material making that, and then the labor and so forth. So that's all figured in on this line. And so then I have to figure competitively what can I sell them for, whether it's $80 or $100 or $350 or whatever competitively I think I can sell these shoes for. And then I'm going to develop a break-even point that says at this many shoe sales, I can then break even. And beyond that is my profit. So if I'm looking at profit, and maybe I'll color that green. So my profit then is this up in here. And the more that I sell out here, the greater my profit is. And so if I'm selling out in here, my profit is going to be this much. Okay, so I've got a cost function, a revenue function, and then I might want to create a profit function, which says, well, my profit is going to be my revenue minus my cost, right? Minus my cost function. So if my revenue function is $80 per shoe, and that's set equal to my cost function, which I said was 300,000 plus 30x. And what I want to calculate then is, well, where does this thing break even? And this is 300,000 here. So I've got this equation, revenue. This is dollars per shoe. And this is cost in dollars per shoe. And we can see that the revenue goes up like this line and the cost is this line. So we have different lines here, but they cross right here. So if I set those equal to each other and solve for X. So let's go ahead and solve this for X. Open your mic and tell me what you get after you solve this for X. And let's have a new volunteer on this one.
I got 6,000.
6,000. Okay, good. And 6,000 what? Is that dollars?
Yes.
$6,000. Anybody agree? Disagree? Can we get a confirmation on that? Is that $6,000 or what are we solving for here?
Shoes.
I'm sorry?
Shoes.
Shoes. So we have dollars, we have shoes. Any other offerings here, what we're solving for here?
I think it's shoes as well.
Shoes, okay. All right, so this is $80 per shoe, and this is $30 per shoe. So those dollars are going to cancel, aren't they? This is dollars, that's dollars. They're going to cancel. So we're going to have then these are dollars. So we're going to have the number. This X value is a number. So this says if we sell 6,000 shoes, so this number here is 6,000. And then the question is, well, what is the break-even point? What will the value of the sales be at 6,000? So if we plug in 6,000 for our cost function here, and we say this cost function at 6,000 shoes, let's say this is 6,000. So the cost function at 6,000 shoes, which is going to be this line here, 300 plus 6,000 times 30. So I'll have 300,000 plus 6,000 times 30. And let's see, what is 6,000 times 30? 30 times 6. That's 180,000. So this point here is at $480,000. All right. So if I sell 6,000 shoes, my revenue is going to be $480,000. So that's this point, 6,000 and 480. This is a quantity, number of shoes, and this is the dollars. So this says we need to build and sell 6,000 pairs of shoes and earn $480,000 just to break even. And then once I've done that, any sales beyond that would be profit. So if I said, what's my profit if I sell 8,000 shoes, I can plug 8,000 into the cost function and into the revenue function, subtract costs from revenue, and find out what my profit would be. Okay, does that make sense to everybody, what we did there? Questions on that at all before we sign off for the day? Okay, if there aren't any questions, that will be it for the day. When am I going to see you next?
Wednesday, Professor.
Wednesday, very good. And let's see, what's the plan for Wednesday? If everybody's taken the chapter 3 test, we'll cover that. If not, we'll cover 7.4, 7.5. Okay, very
Great,
good,
thank you,
everybody.
Professor.
Nice
nice
job.
day.
Nice job, everybody. You worked hard. See you on Wednesday.
Thank you.